Okay, so I'll formally let me do again that thing. So welcome all. So we are now discussing this question, and this is the fourth session. So all right. So question one is about finding the degree of q root 5 plus root 7 over q. So let me repeat again. So you have to find the irreducible polynomial of over q, which will be satisfied by the element root 5 plus root 7.
Let x be root 5 plus root 7.
Sorry.
Take x is equal to root 5 plus root 7.
Okay, so yeah, let's discuss the solution. Let me write x to be root 5 plus root 7 then.
So x minus root 5 equal to root 7.
Okay, x minus root 5 is root 7, right?
So squaring both sides, x
Okay,
squared plus 5 minus 2 root 5x equal to 7. This gives x squared minus 2 equal to 2 times root 5x.
this will give you x square minus 2 equals to 2 root 5x. Yeah, no?
So you are
So you,
getting
mhm.
squaring again.
Yeah, square it again. Again, it will give me, this is the case. Now one can simply look at yeah, so we get this polynomial which is being satisfied by root 5 plus root 7. So the way we constructed, we have anyway chosen x to be this. So anyway, this x is being satisfied with this polynomial. That's correct. But how do we see it's irreducible?
This is
Irreducible polynomial.
irreducible. So we apply Einstein criterion.
Okay, what does Eisenstein criteria says that?
By replacing x by x plus 1.
All right. So now I think things are clear. So using Eisenstein criteria, one can check that this f is in fact um, irreducible over q, and as you can see, what is the degree of this polynomial?
Fourth degree.
It's 4, right? So clearly then the degree of my extension root 5 plus root 7 over q has degree 4. Right? Because we have just adjoined one root, which is the root of this polynomial, and this is an irreducible polynomial satisfied by that root, therefore it has degree 4. This is degree 4. Now we want to list out all the intermediate field. This is the question I think that we discussed last time and somehow we could not solve it nicely. So let me discuss again. So we want to write all intermediate field between q 2 power 1 by 4 and q. So last time we gave an idea that since 2 power 1 by 4 is not a Galois extension because it does not have all of its roots, because the polynomial which will satisfy by this does not have its all roots inside this extension. So it's not a normal extension. So we cannot use the tricks which we know for Galois extension. So Galois extension, we know that there is a Galois group associated and there is a bijection between the subfields and the subgroups. So we went into a long calculations where we went to the Galois group, Galois extension first, and look at all the subfields there. And among those fields, we try to look at what are the subfields lying between Q2 power 1 by 4 and Q. So, however, I find that there is one more simple way to see this thing. So, let's discuss that. So, before that, if you have any idea, I will also try to do that. So, how to see this?
Find the intermediate fields, we apply that fundamental theorem of Galois theory.
Fundamental theorem of Galois theory, right?
That is, we
Okay.
have to find all possible subgroups of the Galois group, and from there we can find out the intermediate fields.
Right. One is that way. Exactly. One is that way. So, if you see, I mean, we have. Let me try to discuss both the ways possibly. So Q 2 power 1 by 4 over Q is not a Galois extension. So we cannot use fundamental theorem. So for fundamental theorem, I need to take the Galois extension. So I will just simply take its, I will take extension which is Galois. So if you see, this becomes a Galois extension. So this is Galois. However, this is not Galois. So we can use fundamental theorem for this extension. So we have Q 2 power 1 by 4 over, sorry, comma I over Q. And here we can see that what is the Galois group. So this is a Galois extension. So it corresponds to some Galois group. So notice the Galois group, I think we discussed last time. That is, if you remember, Galois group of this over this. Do you remember? So first of all, what is the degree of this extension? Can you tell me that?
8.
Yeah, it's 8. So therefore the Galois group has to have order 8. So this over Q 2 power 1 by 4 over Q. We know that this is same as Q 2 power 1 by 4. Joining I to that. So here it's degree at the most 2. This is degree 4. And one can check it's exactly equal to degree 2 in fact. So this is degree 8. Right. So we just one has to just check that I does not belong to Q 2 power 1 by 4. That's enough to say that the degree is 2. Right. Now this Galois group has order 8. So one has to of course check that how the elements are there. So I will simply say that for timing I will say D4. We can see, maybe you can look at the previous recording. This thing we have I think seen that this is actually D4 group and generated by some sigma and some sigma 1, sigma 2, where sigma 1 has order 4 and sigma 2 must have order 2. So such two Galois automorphisms, so sigma 1, sigma 2 from Q2 power 1 by 4i to Q2 power 1 by 4i. Of course, one has to find what are those sigma 1, sigma 2. Sigma 1, if I try to write sigma 1, 2 power 1 by 4 and I, these are the two things one has to just see. And so if you recall that I think this and uh, this should generate my um, this should generate these two the group of automorphisms, and the Galois group actually will come out to be D4. D4 it's a dihedral group of order 8, and you can also see it's non-abelian group, right? So one way is that you try to look at all possible subgroups of D4, and then look at their fixed field. So I'll just try to write the criteria. So criteria is find all possible.
That sigma 1 is 2 power 1 by 4 to 2 power 1 by 4i.
Yeah. You know, the roots of our polynomial x power 4 minus 2. 0 has 2 power 1 by 4 minus 2 power 1 by 4. 2 power 1 by 4i minus 2 power 1 by 4i, right? So if you take minus here, minus 2 power 1 by 4, that will have order 2, right? So if I take, maybe I'll just repeat. If I take sigma 1 to be 2 power 1 by 4 going to minus this, I going to I, then order of sigma 2 is sigma 1 is 1. Because if you apply sigma 1 to again sigma 1 of 2 power 1 by 4, it is minus of this, but you again apply minus, you'll get this. However, you know sigma 1 square I keeps constant. So sigma 1 square is identity. But we want order 4, right? The generators of D4 are order 4 and order 2. So I cannot take this I, but I have to take I. I think it's clear. You can also take minus I. That's also equally same. Right. So these are the two which will generate my group D4. Now we want to see. So we want to see one way is that find all subgroups of D4 and let's say subgroups HIs of D4, and then by fundamental theorem we know that we can get the fixed fields. So if I have Q, K as Q, then we just look at K H I. Right, this will give me subfields of, let's say this is my K, this is my maybe F. This I used to write F, this is K. So FHI gives me the subfields of K. Right, but somehow, you know, writing all subgroups and finding their all fixed fields, it's not that good idea. Of course, this will take some time. You have to keep doing some things. But I still don't feel that this is a very good idea because this is too much to like you will have some many things to do, then only you will find. So first thing is you have to find all subgroups and then you have to find all fixed fields. And among them, you have to check which are those which are sitting inside Q2 per 1 by 4. So it's like a very lengthy process. So one can try, I will write, possibly I will write what are the fixed fields. So if you have Q2 per 1 by 4i and you have Q, so I will try to write what are the all possible subfields lying here and there. So if you see, it is nothing but Q2 per 1 by 4, Qi. Then you have Q2 per 1 by 2. Then I think Q2 per 1 by 2i. Let's write it in a nice way. So like this. I think I will try to write more. So there are many, and among them, checking which one are there, like you have to work out this, and then only you will find that this is the field which is actually we are looking at. So maybe I don't find this as good idea. Let me use some other trick. Okay. So I will use some other way. All right. So one thing is clear that if I look at Q 2 per 1 by 4i, Q 2 per 1 by 4, then Q, then I know that below is our group, right? This is our G, and above is the trivial group. This is clear, right? Because if I take the trivial group, it will fixes everything. So it corresponds here. If I take this group, so if the whole group, if I take, then you know that Q has to, prime field has to be fixed because Q has to be KG, right? This we know. So, okay, knowing all these things, we just want to know what are the possibly, what is the subgroup here. If I know what is the subgroup corresponding to this, things will be easier because then I will be just looking at subgroups here in between because those subgroups will give me subfields here, right? Right. So we will simply look at this thing. So let's look at this extension has degree 2, this extension has degree 4. We know that order of H is same as the degree of q 2 power 1 by 4 I is 2q 2 power 1 by 4. This is okay, right?
Yes.
And therefore, what is the order of h?
Order of which is 2.
Yeah, order of h has to be 2. So if I in between I'm looking, this is order 4. So therefore sub this index of order inside h is nothing but 4. And order of h is nothing but 2. This information I have. This is what we know. Now look at how h has been formed. If I look at the let me look at now. Suppose I try to know the structure of D4, okay? Because this is about group theoretic question now, we want to know the subgroups here in between. So for that, I will just look at the structure of D4. So if you remember, it has rotations and reflections. It has rotation of 90-degree that will generate a cyclic group of order 4, and reflection will be a degree 2 element, right? So if I take 1, R square, R cube, S, S as a reflection, then R S, R square S, R cube S. These are all possible 8 elements, right? 3, 4, 5, 6, 7. Yeah. So this is being written as the form that I have written R comma S. This is generated by R and S because every element is a product of R and S, where order of R is 4 and order of S is 2. This how we write the presentation of the group. This we call as presentation. Right. So we will try to use this fact. So if this group is generated by R comma S, sorry, I'm so sorry. This is the lower group is generated by R comma S. And if we try to look at the order 2 subgroup inside it, then it has to be generated by S, right? If you see, the order 2 subgroup inside my this will be S because of I want the fixed field of Q2 power 1 by 4. Right. So if you try to look at, then S is that group which has order. So if I look, H is nothing but 1 comma S. S is reflection. Then that order of H is nothing but 2. However, if you look at other elements, let's say look RS, the order of RS will not be 2, right? RS. If you look at, you will see that that order will not be 2 because of some, because it has one more way to see RS, R inverse is S inverse. So use such criteria to say order 2 element, order 2 subgroup will be this. Now we want to know which is that subgroup which is sitting inside this H and this D4. That means I want to know which is that subgroup which lies between S and R comma S. If you see, the only subgroup which will be is nothing but generated by R square comma S, because um, among so this is contained inside that group which we want, therefore it should contain an element outside reflection. That means it should contain rotation, but we know that rotations are um, if you take R, then R is generator for rotations, so you have to take all four: 1 R square, R cube, and if you take this together with S, you will get all. Therefore you should not be taking R, or you should not be taking R cube, because R cube is also a generator. So therefore, you cannot take 1, you cannot take R, you cannot take R cube. The only possibility you have to take is R square comma S. Because this will be just 1 R square S R square S. Only possibility. Moreover, you also see that this is order 2 subgroup, this is order 8 subgroup. The only subgroup which can lie should have order 4. So you can also see that what order 4 subgroup can lie. So this is nothing but that order 4 subgroup which you are looking. Right. Now we just have to know the fixed field by this subgroup. Once we know this, then we are done. So let's look at that. I think I should be able to write in terms of sigma is, then only things will be clear. So, hello? Till this point, is this everything fine? Hello?
Yes, listening.
Okay. This is clear, right? Till this point?
Yes.
Okay. Now, let me tell you how this R and S I'm relating with sigma is, right? Because my group is sigma 1, sigma 2 up to sigma 8. And we have written sigma 1, sigma 2, the generators like this, right? This is our sigma 1, sigma 2. So therefore, this is my R. And if you see, this is my S. So let me write again so there should not be any confusion. So for me, G is D8 generated by sigma 1, sigma 2. And here I'm writing it to be R, comma S. So just read everything in terms of that. Sigma 1 you will write as 2 power 1 by 4 going to 2 power 4i. And I going to I. And sigma 2, maybe this you see as R, this say as S. This will go to same, but I going to minus. Right. Now let's look at the fixed field by R square comma S. So you try to see sigma 1 square. What is that? 2 power 1 by 4 going to where and I going to where? Can you tell me where sigma 1 square maps 2 power 1 by 4 to?
2 power 1 by 4 to 2 power 1 by 4 times I.
Yeah, sigma 1 will map
After
2
that,
power 1 by
2
4.
power 1 by 4 I
Hmm?
goes to 2 power 1 by 4 I into I. So minus
Yeah,
2 power 1 by 4 will come in.
exactly. This is this. And I will be fixed. I is anyway fixed, right? Now look at S. So we are looking at generated by R square comma S. S is nothing but sigma 2. Sigma 2 is mapping 2 power 1 by 4 to 2 power 1 by 4. I going to minus I. So let's look at what are the elements which are being fixed by these two things. So a general element of our field, how does that look like? Can we write that? So we look at a general element of our field Q 2 power 1 by 4 comma I. How does that look like?
A plus B times 2 power 1 by M plus C
Plus C.
I.
Okay. So if you try to like this, then let's write that. But in this way, you will not be able to somehow see the thing. So maybe I'll try to write, you know, Q 2 power 1 by 4 over Q has the basis. If you see this as an extension, the basis is 1, 2 power 1 by 4, 2 power 1 by 2, 2 power 3 by 4. This is a degree dimension 4 extension. Therefore, the basis should have 4 elements. And you want one more, right? You want I also. So you want to extend that. So therefore, any element, if you try to write, then it should be of this form. This is what I want to say. A plus B, 2 power 1 by 4. Let's say A1, A2. A3, 2 power 1 by 2. A4, 2 power 3 by 4. This is same as 2 power 2 by 4. Plus A5 times I. Although there will be several many, in fact, I should write everything. 2 power 1 by 4i. A6, 2 power 1 by 2i. A7, 2 power 3 by 4i. And A8i. This is how 8 coefficients will come as looking at 8-dimensional vector space over Q. Do you follow this? I think this will take some time. So this is okay. This is a writing element. So maybe let me repeat. Okay, let me repeat. So we have this extension to this over I, and we know the dimension is 8. So therefore, I should have a 8-dimensional vector space over Q, right? Now, notice that the elements which are here is nothing but the way you see the roots, right? So if you see the roots, so 2 power 1 by 4 going to 2 power 1 by 4 plus minus I, and 2 power 1 by 4 going to 2 power 1 by 4, and I going to plus minus I. So here, we try to see the basis. So it is nothing but extension of this with the I. You are extending this with I. So first write this as a vector space and write its basis and then multiply with I. So you have 1, 2 power 1 by 4, 2 power 2 by 4, 2 power 3 by 4. This is a basis for q 2 power 1 by 4 over q. But now you are taking I also. So then you have to take the I factor also and you just have to multiply with the I. So u 2 power 1 by 4 I, 2 power 2 by 4 I, 2 power 3 by 4 I, and I. This will complete the list of all basis elements of this as an extension over Q. Is this okay somehow? Just like adjoining, this to this will give a basis from this. And then you are adjoining this, that will give you this. Because you see Qi is nothing but A plus Bi, where A and B from Q. But if I write Q 2 per 1 by 4, then it will also mean that it is A plus Bi, such that A and B from Q 2 per 1 by 4 now. But how the basis of this is that you can write any element A like A0 plus A1 2 per 1 by 4, A2 2 per 2 by 4, A3 2 per 3 by 4, right? You can write any A like that. Substitute this, you will get what we want. Do you understand?
Yes.
Okay. Now, noting all this fact now, because of this fact now, one can write any general element of Q 2 per 1 by 4I as like this. A0 plus A1 2 per 1 by 4. First take all powers of 2 per 1 by 4 and then multiply all the powers with the I because of this fact. A4, I, A5, A6, A7. I think we are done because we started with A0. So we have eight many elements, right? Now let's apply. Uh, we want the fixed field by sigma 1 square and sigma 2. This is my R square, this is my S, and the group generated by that is nothing but R square comma S. So we want which is fixed by sigma 1 square and sigma 2. Let's write. Okay, sigma 1 square is 2 power 1 by 4 going to minus 2 power 1 by 4 I going to I. And sigma 2 is 2 power 1 by 4 fixed but I going to minus I. Now let's check what are the elements which are being fixed by both. This is what we want, right? Fixed field by sigma 1 square sigma 2. This is some subgroup. We want Q of H prime. This we want. Q is my FH prime, like that. Now, 2 power 1 by 4 goes to minus 2. So this has been changed. Just realize the changes. Just realize the changes. This will not change. This will not change. This will change to minus 2 power 1 by 4. This will change to minus 3 power 1 by 4. This will change by sigma 2. These will be changed by sigma 1 square. This will be changed by sigma 2. This will be changed by sigma 2. This will be changed by sigma 2 again. This will be changed by sigma 2. So what is the thing that is just fixed by both? Can you see that? Recognize those things.
But the fixed field notation is A power H dash or F power H dash.
I think this was F I changed, right? Yeah, this is my F. F is my Q. Right? We want F H I. This we want. You understand, right? Now? Okay, let me just repeat once again the fundamental theorem. Okay. Let's go back to the previous tutorial and let's look at the fundamental theorem. Yeah. So fundamental theorem says that if you have K over F, I have also taken K over F. K is my upper field, F is my lower field. Then given any H subgroup, you should be getting KH. And for, oh sorry, KH, I wrote FH, right?
Yes.
All right. This is the issue. Okay, so let me change. This is KH. This Q 2 power 1 by 4I, its whole power H. Right. Sorry. So what if you observe that through sigma 1 square and sigma 2, what are the things both together will not change? What is that remaining among these elements? What is the thing which will not change? So notice that this will never change, right? This is never changing. This is changing. This is changing. This is changing because of I. Sigma 2 change I to minus I. So those having I will not be fixed. And those which are independent of I, that will be changed by sigma 1 square 2 power 1 by 4 going to minus 2 power 1 by 4. So this will be changing. This will be changing. I'll write how it will change. So if you see this and sigma 1 square, send it 2 power 3 by 4 to sigma 1 of sigma 1 2 power 3 by 4, which is sigma 1 of 2 power 1 by 4 whole cube. 2 power 1 by 4 goes to minus 2 power 1 by 4. Its cube is again minus 2 power 3 by 4. And now again this is minus of sigma 1 2 power 3 by 4. Now this is minus sigma 1 2 power 1 by 4 whole cube, which is nothing but, can you see that? This is minus 2 power 3 by 4, right? So just the element a naught plus a1 a2 2 power 1 2 by 4, which is same as 2 power 1 by 2. So if you see a naught plus a2 times 2 power 1 by 2 is the only elements which will be fixed by sigma 1 square and sigma 2, where a naught is a naught both from Q. So what is the field then that will become? Yeah, can you say something?
Q of 2 power half.
2 power half, right? So if you see then this is the only field, right? Because of only subgroup that you have between H and D4 is this only. So knowing the only subgroup lying between this is the only fact which is helping us. So knowing that this has order 2, this is order 4. So in between we have order, sorry, this is order 8, this has order 2. Knowing that the only subgroup which can sit in between is order 4. And there is only one order 4 subgroup that will give you that there is only one subfield between there, and that is nothing but Q2 power 1 by 2. So with this, I think I'll write that only field between this and this is Q2 power 1 by 4, Q2 power 1 by 2, and then Q. So total are 3 intermediate fields. This is okay. I think this is more better than, I mean, you should have gone through various subgroups. This is one subgroup which we dealt, and then we find a fixed field. But for general, you have to find all subgroups and then their fixed fields. That is more messy. I think it's fine, right? Should I repeat anything that you want?
It's okay, madam. One should be thorough with the diagonal group.
Yeah. I mean, one has to just look at the group itself and their properties. That will be useful. Yeah. Okay, so another question is about knowing that extension is cyclic. So first of all, what extension we say is a cyclic extensions?
Cyclic extension, there are two conditions to be satisfied.
Okay, so what are those? So recall an extension, let's say a finite extension. We talk about finite only. Finite extension P over F is cyclic if
K over F is Galois.
Exactly. It has to be Galois first of all.
And that Galois group is cyclic group.
Exactly. If the Galois group is cyclic, then we say the extension is also cyclic. Very good. Now, can we say that the given first extension is it cyclic?
The Q of root 2 or root 5.
It's yeah, it's like something like that. Root 2, root 5, root 2, root 3, root 3, root 7.
Yes.
Yeah, same thing. There is nothing special about 3 and 7. You can take 2, 3, 2, 5, 3, 5, 3, 7. First of all, is it Galois? Let's look at, is it Galois? Which criteria will you choose to say that is it Galois?
It is a splitting field of a separable polynomial.
Yeah, what is that polynomial? The splitting field of.
Or we can prove that the dimension of K over F.
Yeah, what is the dimension?
Dimension of K over F is 4.
Yeah, it's 4. So we have this extension has degree 4. Now, how do I say it's Galois? Looking at the Galois group, right? I mean, you look at the group of automorphisms. So if you look at the group of automorphisms from root 3, 7 to root 3, 7, then you will notice that you have 4 because you have root 3 have plus minus root 3 two choices. This has two choices. So totally we have 4 automorphisms. Therefore, you are saying that this extension is same as the group of automorphisms. So therefore, maybe I should write this way. Yeah, therefore, this is a Galois. Yeah, a Galois extension. Of course, you can say through this splitting field of this polynomial. It's a Galois extension, right? All right, so it's a Galois extension. So now, is it cyclic? That means the Galois group is cyclic or not. So can we check that? So what is the Galois group? So we have sigma 1, sigma 2, sigma 3, sigma 4. Let me write. This is identity. This will mapping root 3 to root 3, root 7 to root 7, minus root 7, root 2 minus root 3, 7 to 7, root 3 to minus root 3, root 7 to minus root 7. Yeah, if you look at then looking at the order of these automorphisms, can you say is it a cyclic group? The order is 4. Either the group is Z2
There
cross.
must be an element of order 4.
Yeah, there should be an element of order 4, but does it have?
In Z4, you have an element of order 4.
Exactly. This is a cyclic group of order 4, yes. But if you see our group is sigma 1, sigma 2, sigma 3, sigma 4. What are the orders? This is order 1. This is order.
They're all order 2.
They all are order 2, exactly. So what do you say? The group is this, right? So is it cyclic group? Is Z2 cross Z2 cyclic? No, right?
Yes.
Because this, yeah, so this is not, because this is not a cyclic group. This is just a abelian group. However, this is a cyclic group. Right. So in this case, I will write this is not a cyclic extension, not cyclic. What about this extension Q omega over Q, where omega is the primitive third root of unity? So let me write. First of all, is this extension Galois, where omega is primitive third root of unity. What is the dimension? What is the degree of this extension?
2.
2, exactly. And what is the irreducible polynomial?
1 plus x squared.
Exactly right. This is the irreducible polynomial satisfied by omega. Right. Now, what we are looking for, we are looking at the Galois group. So is it Galois? First of all, is it Galois? I'm saying there is no need to check is it Galois or not. Can you justify why?
We have to find what are the elements in the Galois group.
Yeah, but I'm saying that you don't need to check. In this specifically in this case, you don't need to check anything to say that it is Galois.
What you'll have to see is whether this f of x is separable.
Yeah, you can say that way also. So of course, these roots of this are nothing but omega minus omega or omega omega square. Sorry, omega square, not minus omega. So clearly both roots are there. So you can say it's a splitting field of this separable polynomial. Yes, you can say that way. But I'm saying that you recall the previous result that any degree 2 extension over characteristic 0 field is always a Galois extension. This is important. So wherever the degree 2 extension come over Q, it's always Galois. So this is just recall. All right, so it's a Galois. Anyway, it's a Galois.
Any degree 2 extension over characteristic not equal to 2.
Yeah, I mean, I'm saying characteristic 0, that is also equally not equal to 2, right? I'm using one consequence of that. Yeah. So characteristic 0, of course, is not equal to characteristic 2. So, right. Correct. So therefore, this is a Galois extension. Now, knowing that it is Galois, we need to check is it cyclic. So what do you say? This is okay, right? If this is true, then what is the group?
So in the previous problem, we got not cyclic, right?
Yeah, previous we did not get cyclic. Yes, it was not cyclic because your Galois group was not cyclic. What do you say here? So what is the order of the group, Galois group?
It's 2.
How many order 2 group elements? I mean, how many groups having order 2, you know?
Only G.
Only Z2, right? And that is cyclic, right? So, and we know that any group of prime order, of course, finite group of prime order has to isomorphic to Z by PZ, right? Do you agree? And this is a prime, P is 2. Therefore, it has to isomorphic to this. This is not true for if it is not prime, means if you see for order 4, you will see it is just Z2. This can also be possible, which is not cyclic. So this is not prime. But if you have any prime order, let's say 7, that has to isomorphic to Z7, right? So these things we are useful to say that the group here is cyclic. So therefore, in this answer, this extension is a cyclic extension. Is it okay, right?
Yes.
Okay. Now we will move forward to third question. What is the degree of Q 2 power 1 by 4 zeta 8, where zeta 8 is the primitive eighth root of unity over Q, and is it a Galois, and find the Galois group. So let's look at first this primitive eighth root of unity. I think this discussed will we discussed last time. So zeta 8, a primitive means uh, order is 8, exactly 8. It's not less than 8. So knowing that, you know that these are all eight roots of unity. Among these, you will see that there are some of them which are primitive. Can you see which are those which are primitive, which have exactly order 8?
For those values of k which are co-prime with 8.
Exactly. So E 2 pi I, I'm taking k to be 1. This will get you this. Then this, and this. You will see expanding that. These are nothing but, if you see this one, this is nothing but cos pi by 4 plus I sin pi by 4. And if you see all, they are related. These are just plus minus of this. You see. So all the roots are exactly like this. These are all 4 roots. Okay, now let me take this one. 1 by root 2 plus I by root 2. All are equally good. I will take this one. Now, we want to know the degree of Q 2 power 1 by 4, comma, this primitive element 1 by root 2 plus I by root 2. Can you simplify this extension? Note that 1 by root 2, is it in Q 2 power 1 by 4? Can I say?
Yes.
Yeah, because 2 power 1 by 4 is contained in our Q 2 power 1 by 4. Its a square are also there. And its inverse are also there. Square is nothing but this, which is nothing but this. And inverse is also there, which is nothing but this. So I can simply remove these two things. Now, what can you say? 1 is also there, right? In Q2 power 1
Yes.
by 4. So I
So
can
2 power 1 by 4 comma I.
exactly. And this we have checked, right? So all the things are known for this. This is Galois, and its Galois group is what is the extension degree?
Degree 8.
Exactly, it's 8. Degree 8 extension, and of course, this Galois group also we discussed. Like, what is the Galois group, if you remember? T4, right? Dihedral group of order 8. All right. So, when you have smaller orders, then not various possibilities of group, So, you know that if you have abelian group, then the possibilities of order 8 are this or this or this. These are possibility when your group is 8 or order 8 by fundamental theorem of finite abelian groups. But if your group is not abelian, then not various choices are left. So you will first try to see D4 itself. So this is how we see. All right, so this question is more or less done. So question 4 is write all the intermediate fields between Q root 5 root 7 over Q, and is it Galois? Can you see something? All right, let me discuss this. This we have checked. The similar kind of question I think we have checked. First of all, what is the degree? And then we will look at the corresponding subgroups. What are the degrees of these fields?
2 and 2.
2 and 2. And therefore total is degree 4. Is it Galois? This is Galois, right? This is Galois. I think I will use other pen. This is Galois because the extension degree is same as the group of automorphisms. Group of automorphisms where you will have the choices for this and this are 4. So total 4 automorphisms. Or it is the splitting field of which separable polynomial? So I can realize this is a splitting field of some separable polynomial. What is that?
Already you have calculated that one.
Yeah, so it's x square minus 5, x square minus 10. Product of these two. Yeah, so
X power 4
x power 4,
minus
okay.
24x squared
24x square
plus 4.
plus 4. Is it the same extension? I doubt. Root 3, root 7, right? That is different. Or root 5, root 7, the same one. I'm not sure. Okay. No, but okay, then there is one thing. You told me about root 5 plus root 7, right? You told me about this. This.
Yes.
But are they equal? Is this equal to this? You can say that, provided you can say that these two extensions are same. Or these two fields are same, in fact. Can we say that these two are same? What do you feel? Are they same?
Root 5 q of root 5 comma root 7. So the second one is contained in the first one.
Exactly. Correct. Q root 5
Second one.
plus this is contained in this. Why? Because root 5 belong to this. Root 7 belong to this. And since it is a field, therefore root 5 plus root 7 also belong to this. Q also belong to this. Therefore, the field generated by sum is also contained. Exactly right. Now, can we use the degree field degree knowledge to say that these are equal? So recently you told me that this extension over Q has degree 4, right? Because of irreducible polynomial. This is what we did in the first question. Because of irreducible polynomial has degree 4. But this is contained in Q root 5 comma root 7. But the degree of this is also 4.
So the degree 1, so they are equal.
Exactly. This has to be degree 1. This implies Q root 5 plus root 7 always equal to this. In fact, this is true for any root A, root B. For A and B, root A, root B are linearly independent. I will say something about this in the end, linearly independence. This is a very important thing. Anyway, so then, yeah, our question was now, anyway, we have deviated. So yeah, we want to find the intermediate fields between this. Right. So we got that it is a Galois extension and we want to know the intermediate fields. So for knowing the intermediate fields, being a Galois extension, I can use the fundamental theorem of Galois theory. Now, in order to find the fixed fields, I have to find the subgroups between them. So if you see, okay, so the group here is nothing but the trivial. Always this corresponds to trivial, this we know. This corresponds to the whole group. So what is the Galois group? That is also being discussed several times. What is the Galois group here? So for this extension, this is Galois we know. What is Galois group? Look at the automorphisms, look at their order, and look at the group order. The possibilities are Z4, cyclic group of order 4, or Klein 4 group, Z2 cross Z2. What do you say? Z2 cross Z2, right?
Klein 4 group is not cyclic, right?
Yeah. It's not cyclic, of course. This is Klein 4 group, not cyclic. We are not saying this is a cyclic group, but Q root 5 over Q is a cyclic. This is a cyclic extension. This is not a cyclic extension. Because its Galois group is not cyclic. It's just Z2 cross Z2. All right, so I think let's move to finding the intermediate fields. This is our main goal. Yeah. So group is Z2 cross Z2, which you can also write as, maybe we will write in terms of our automorphism. Sigma 1, sigma 2, sigma 3, sigma 4. Sigma 1 is identity. This is sending root 5 to minus root 5, root 7 to root 7. Root 5 to root 5, root 7 to minus root 7. Root 5 to minus root 5, root 7 to minus root 7. All have order 2. Everything has order 2. So it's isomorphic to Z2 cross Z2. So how many subgroups can you possibly form from this group? The group has order 4. And we have a trivial group between. How many possible subgroups that we have?
Sigma 1, sigma 2, sigma 1, sigma 3, sigma 1, sigma 4.
Anything else?
And the G itself.
And G itself. And identity, of course. So if we check, these are the all possible subgroups that we have for Z2 cross Z2. If we try to see in terms of Z2 cross Z2, we can see like this also. Z2 cross identity is one group. Identity cross Z2 is another group. And 1 cross 1 is also a group. If you see, if you write Z2 as 0, 1, then if you take 1, 1, then it is also order 2 because it has order 2, this has order 2. Yeah, so we have three groups, not cyclic also. Yeah, so we have three subgroups. So let me write this subgroup as H1, this is H2, this is H3. And we write, I think we will write here. So this is one field. We want to know the all possible field here. As subgroups are 3, so I will write three boxes. So H1, 2, H3, all are subgroups. Let's say corresponding to H1. H1 is this, sigma 1, sigma 2. What will it fix? Root 5, it will change. What will it fix? Root 7. What is the fixed field? Can you guess? So it does not fixes root 5, but it fixes Q and root 7. So what is the fixed field? So, okay, if you this is not okay, I think I'll try to write up the bases now.
But
So, yeah,
q of root 5, q of root 7,
yeah.
q of root 5 into root 7.
Oh, you have computed. Good. So this will fix root 7. So it is q root 7. The fixed will be this. For this, the fixed will be root 5. But for this is not clear, right? It's not clear. Very obviously is not clear. But if you try to write the basis element, so basis is root 5, root 7, and root 5 into root 7. This is the basis for q root 5, root 7 as a vector space over q. So you will see this product will be fixed. These elements will not be fixed, but the product will be fixed because both are negative. As a product, it will be fixed. So sigma 4 will fix is, so I'll just fix now, fill up the boxes. This is Q. So, okay, H1, H2, H3. Okay. So this is Q root 15, sorry, 35, Q root 5, I think, Q root 7. Yeah, so we write then Q root 5, Q root 35. So we have how many? We have fields now total intermediate. So we have total intermediate fields. Total we have 5, right? So I think this question is also done. Now let's move to. So we have given a Galois extension such that the Galois group is. I have taken this question from what the problems I have discussed in the lectures. So I have just taken this problem because I find it really nice. So I just want to discuss in detail this. If you want, we can discuss. If you don't want, we can leave it.
Discuss.
Okay. So, all right. So we are given a Galois extension whose Galois group is isomorphic to Z2 cross Z12. So what is the order of the group first of all?
24.
24. It's 2 times 12, so 24. So one thing we know, our group has order 24. Now, also we know that K over F is a Galois extension. So what is the degree of the extension therefore? Which is L over F.
A over F is 24.
Yeah, it's 24. We have an intermediate field given to us. Let me write that now. A over L is to F. This is 24. And find the number of intermediate fields L. We have to find how many L are there such that the degree L over F is 4. So if this degree is 4, what is the above degree? This is 6, right? This has degree 6. Now, we know by fundamental theorem of Galois theory that any intermediate field, suppose this has order 6, then this should correspond to some subgroup H of G such that order of H is 6. Do you agree? So recall you have K over L over F. So L is anyway given by some KH. This has to be some, there exists some H such that this should happen. And this extension is same as order of H. This extension is same as index of H and G. This is because of fundamental theorem. So therefore, our order of the group should be order 6. That should correspond to L. And L is nothing but the fixed field of H. This at least we know that. Now, if we try to know the intermediate fields for this, then maybe I'll write a statement. So number of fields lying between K and F such that L over F is 4 is same as number of fields lying between K and L such that K is to L, or maybe K and F, I should say. Number of fields L lying between K and F such that K and L is same as 6. This is equal, right? Once you have this 1 degree fixed below, above degree is fixed. So either of the knowledge of above extension or the lower extension is enough to know the L. Either you see in above extension or you see the below extension. The things will remain same. Now we just want to know subgroup of order 6. So we want to know, in order to know L such that K over L is 6. This is same as we want to know how many subgroups H of G such that order of H is 6. This is okay, right? Because of this knowledge. In order to know the lower thing, we change our statement to going to upper extension. Upper extension means that you should be able to get a H such that order of H is 6. Then only you will get a upper extension with the dimension 6. This is okay, right?
Yes.
All right. Right. So the all question has been reduced to finding number of subgroups of G having order 6. So let's try to find the order 6 subgroups. Now we know order of H is 6, either it is abelian or it is non-abelian. If it is abelian, then it is isomorphic to Z2 plus Z3, which is same as Z6, right? Because these are co-prime. So I can write because of this result. If you are familiar with this, then abelian, that has to be a cyclic group. Non-abelian has to be isomorphic to S3. This is the smallest non-abelian group we know. And you can also notice that D3 is isomorphic to S3, the dihedral group of order 6. Sorry. So order 6 is the smallest non-abelian group, and that is S3. So either it is S3 or it is Z6. Since we are looking at subgroup H of this group, Z2 cross Z by 12Z, is it allowed to be non-abelian? Can we take H to be non-abelian? Is this group abelian?
Yes.
Can you have a subgroup of abelian group non-abelian?
No.
No, because every subgroup of abelian group is always abelian.
Abelian.
So H cannot be isomorphic to S3. This for sure we know. So therefore H has to be Z6. Do you agree? Now knowing this, we just want to know how many subgroup of order 6 lies in this group. So how many, question is how many order 6 elements. So knowing order 6 subgroup is changed to how many order 6 elements in G lies. Is this same? If I answer this question, will I be able to answer that how many subgroup are there?
You can generate each element to get
Exactly right. Exactly. So there is one reason that if element of order X is this inside a group, then the group generated by X has order N. Knowing this fact, this will help me to get number of order 6 subgroups. However, there can be possibility thing. One possibility is there that two elements can generate the same group. You understand? Let me write, okay? So our group is Z2 cross Z12. So here the elements are 0, 1. Here the elements are 0, 1, 2, 11. Operation is mod 12. Operation is mod 2. Now, if I try to see how many order 6 elements in this group, can you try to give me order 6 elements? Of course, your elements has to be tuple A, comma B. A have you have to choose from here, B you have to choose here, such that order of A, comma B is 6. Can you tell
Is
me
the
that?
LCM of first element, LCM of
That's
order of the first element, comma order of the second element.
exactly right. So now, since you know order of 0 is 1 and order of 1 is what? 2, right? Order of 0 is 1 and order of 1 is 2. Because you have to sum 1, 2 times, then only you will get 0 as identity. Right. So if I choose 0 as an element, first element, what do I have to choose in order to say that the order of that element is 6?
Should be 2.
First of all, 2.
2.
Any other element?
I think 4.
4 will have less order, right?
Order 3.
3 will have again order, not 6. If you see 3, 6, 9, 12, 12 is 0. It's order 4. If you look at 4, 4, 8, 0. It has order 3. You need order 6. Order 3 is not there, 4 is not there, 5 is co-prime to 12. So those are co-prime, they have order 12, right? So let me write 1, 5, 7, 11 have order 4, 12. Now what are the things left? Look at them. 3 is done, 4 is done, 5 is done, 8, 9, 6, 8, 9, 10. 6, sorry, 6 and 10. Even 6 is also done. Because 6 and 0, 6 has order 2. If you look at 8, 8 has order 3. What is left? 1 is done, 2 is done, 3 is done, 4 is done, 5 is done, 6 is done, 7 is done, 8 is done, 9 is done, 11 is done. What is left? Ten is left, right? So, okay, maybe let me repeat. Maybe you might have lost. Um, order of 1 is 2. Order 1 here is order 12. Order
Yes.
5, order 7, order 11 is 12. So I'm not looking at these orders. 3 has order 4, 3 is done. So 1, 2, 3 is done. 4 has order 2, it is also done. 3, so it is not of order 6. 5 has order 12, it is also done. 6 has order 2, it is done. 7 has order 12, it is done. 8 has order 2, 3, if you see from here, order, it is done. 9 has order 4, if you see, it has order 4. 9 is done. 10 is left. 11 has order 12. So, just 10 is left, which has order 6. So, this element and this element has order. They have order 6. But can you see there, the group generated by both the elements are same. This is what I want to say. Even if there are two distinct elements, but the group generated by them is same. What is the meaning group generated by? Let's write that. So group generated by this is nothing but you have to add up this element all the time. Add up this element with itself. What will you get? 0, 4. Next, you will get 0, 6. Next, you will get 0, 8. Next, you will get 0, 10. So, you know, 0, 10 has already come here. So this should tell you that this is same as 0, 10. This should tell you itself. Because if you take 0, 10 with same 0, 20, but you are working in Z12, this is Z12, modulo 12, it will be 8. So you will get back all your elements. So therefore, these two groups are same. Now you have taken 0, then you got this. But if I take element 1, comma B, what is that B? So that the order of this is nothing but 6. This has order 2. What should I choose this as order?
LCM 3.
Yeah, you can choose 3. You can also choose 6 also, right? So order of B is what is allowed. It is order 3 and order 6 are allowed. Is it okay?
Yes.
So what are the possibility?
1, order 3 element is 4.
That is 4. Yeah, 2, 4. Sorry, 4. Anything else? You can look from previous, which has order 4. B has order 4. This has order 4. 9 has order 4. That's it, right? So, 9. Order 6 you have already seen. It's 1, 10 and 1, 2. This is okay, right? Now, if you see the group here, it is nothing but 1, 4, 1, 2, 8 means 0, 8. 1, 4 means what do you say? 1, is that 0? And then you write again, then you will get 0, 0. This is okay, right? Forgot to write 0, 0. This is okay, right? The group
Yes.
generated by 1, 4. Okay, but we want group of order 6, right? What happened? The same of some. Did we make some mistake or? This should be okay, right? 1, 4, 0, 8, 1, 0. Ah, next is 0, 4. I'm sorry. You have to write, you have to add 1, 4 to it. This becomes 0, 4. Again, you add this 1, so you will get 1, 10. You'll add 1, 4. You will add 0, 4. Then what will you get? 1, 4. You'll get 1, 8. And then once you add, I think 0, 0. 2, 3, 4, 5, 6. Yeah, this is okay. This is okay. Since 1, look at 1, 2. What do you say? That will be 1, 2. So next is 2, 4, which is 0, 4. Next is 1, 2. That is 1, 6. There is 1, 2, 0, 8. Then again 1, 2. That is this. Again 1, 2 is 0, 0. 3, 4, 5, 6. Right, this is group generated by 1, 2. Can you see any other group? 1,10 has been come here, so this will cover. 1,2 has been covered, so this is covered. Okay, 1,9, does it have order 6? Let's look at 1,9 order. LCM of order of 1, order of 9. Order of 1 is 2, order of 9 is what? This is order 4. So it will not, that's why it's making
Order
issue. Yeah. So then this should not come. Only list is this. So therefore, how many subgroups we get? Distinct one. This one, this one, this one. Any other? No. So total subgroups, elements were many. Elements were many, but subgroups are 3 only. So total subgroups of order 6 are 3 many. Is this okay? All right. Therefore, how many, this will answer you how many subfields are there with this extension. This answers, right? Why it answers? Let me repeat. We want
Why?
to know how. This is fine. Okay. Let's go to point number 2 where we want to know the subfields where extension L over F is 9. Can you find any intermediate field with L over F is 9? Let me write this question. L over F, I think K over L over F. If has degree 24, does there exist L such that L over F is 9? Suppose this is 9. Is this allowed?
Not allowed. 9 does not divide 24.
So, by tower of fields, you should get this. Therefore, L over F should divide 24, which is not the case. Therefore, answer is 0. Okay, let's go to the third point, which says that Galois group of K over L should be the cyclic group of order 4. It's K over L. K over L. That means this time they are demanding that this should be 4. K over L should be 4. If this is 4, then this should be 6, right? So we are actually trying to find how many subgroups are there of order 4. This is same as saying how many subgroups of G of order 4. Do you agree? Answering this is same as this.
Yes.
All right. So
As
we
in
are
the
now
previous case.
sorry. Yeah, same as previously. We will find out how many subgroups of order 4, but subgroups leads to how many elements of order 4. So I think this is just a repetition, so I will not do this. Let's go to the another question. Suppose if a group with every known identity element has order 2, prove that it is abelian. Can we prove that it is always abelian? Yeah. Do you have any idea how to see this?
Every element other than identity is of order.
Yeah. All right, so let's do this. Suppose you take A and B in order to prove that it is abelian. What do you want to prove? Yeah, in order to say abelian, what do you want to prove?
So you take any two arbitrary element and try to prove they commute.
Yes, we want. Moreover, we can say that this is same as. Is this okay?
Yes.
This is same as. This is okay.
Inverse
If you
universal law.
yeah, so okay. Now, can you simplify something? I want you to prove that what is A inverse, what is B inverse. Can you give me that?
They are the same element.
Yeah, why? Because of a order of A is 4.
Every element is of order 2. E squared is
Exactly.
also E.
Right. So therefore, we can get here that it is AB time A inverse is A, B inverse is B. Now, can we say something?
The last one is valid.
Last one is
True.
this is true. Why? This is
AB
all
into BA
square.
equal to E is true. Therefore, AB equal to B.
No, I'm sorry, I didn't get. Can you repeat what you said?
The last expression
Hmm.
AB into BA equal to E is a valid expression.
This is a valid expression.
Yes, because AB squared A, B squared is E, again A squared is E. So the
Okay, maybe
last
simply.
expression is a valid expression.
Yeah, if I say this is this correct, right? This is more simplified way. You can write
Yes.
this whole thing is this. You know that A and B are in elements of G implies this is also an element of G, and every element has order 2. Therefore, this is true. So everything is true. That means we have made if and only if. So that means finally AB is BA if and only if AB square is identity, and which is true. Therefore, AB is BA. All right, this is some simple thing. So this will be used somewhere in the note lectures, though I repeated therefore. Okay, now suppose we have a group of order n and we have same property number 1, which just we now proved every non-identity element has order 2. Then how many subgroup of G has which has order 2? Can you say? It's very easy. I'm just using some tricks somehow.
Please repeat the question.
Yeah. Question is if you have a group of order n and the group has same property which I have written in the point number 1. Suppose point number 1 holds for the group G. Then how many subgroups of G are there of order 2?
G of order 2.
Yeah.
Anything to do with Cauchy's theorem?
Nothing has to be, I mean, done to the Cauchy theorem. It's the simple thing that you will see from the group itself. Maybe I'll write, then only you can get it. So suppose my group is 1, G1, G2, Gn minus 1, and therefore group has order n. I'm saying that all Gi square is 1. Tell me all Hi's such that hi has order 2. How many are there? Can you see that? I think it's easy now.
Because identity along with any one of the GIs.
Exactly. Exactly. So there are n minus 1, right? Subgroups of G of order 2. Exactly. So this will be helpful somehow when you use the fundamental theorem of Galois theory to certain questions in order to know the subfields. All right. So another question is now similar property that we have now. I'm using now previous question to say something now. If Galois group of K over Q is order 32 group and every element has order 2 except the identity in the Galois group, and extension is a Galois extension, let's say I'm writing normal. How many extensions L over Q are there with K over L as index 2? I mean, not index, the degree extension of L over K is 2.
The condition sigma squared equal to 1 for every sigma not equal to 1.
Yeah, not equal to identity.
Why? For identity also it is valid.
Yeah, I mean, no, maybe I'll try to say something else. I mean to say order of sigma is 2 for all sigma not equal to 1. This is okay, right? Notice so I have given K over Q is a normal extension. What can you say about this extension? Given this is normal, what can you say about K over? Yeah.
K over Q is normal if and only if the other two are normals, right?
No, sorry, that is not correct because if you see Q2 per 1 by 4, it's not even. Yeah, separable, it's true. Exactly. So this is normal. You see, this is also normal. This is not normal. Anyway, so knowing the complete one is normal, what can you say about the above one? Above one. If K over Q is normal, well, this normal is very useful thing. Can you say about K over L something? This is also normal. Lower one may not be normal, may not be. But above one will always be normal. Why? It's very easy fact. If some polynomial over Q splits in K, then same thing happens for L also, right? If K is the minimal splitting field of certain polynomial over Q, then that polynomial is also a polynomial over L. So therefore, K is the splitting field for the polynomial over L also. So it is easy. So K over L is normal. That's not an issue. Now, if you know K over L over Q, and you know the Galois, it is a Galois extension. This is given to you. It's a Galois extension. Or even if it is not given, then it is normal, you know, and it is characteristic zero field. So therefore, it is separable. Therefore, it is Galois. Now, using the tricks of Galois extension, we have this group. We want to know there is a group here which we don't know, but its order is 32. We know there is, sorry, here it is trivial. Here the group is 32. In between, we want to know how many L are there such that K over L is degree 2. This degree we want to be 2. This is same as knowing that L has to be fixed field of some subgroup and order of that subgroup has to be, can you say about order? K over KH is same as order of H. Exactly. Therefore, order of H has to be 2. And now, can you say how many order 2 subgroups are there? Because you just had to tell how many extensions are there. This is easy, right? How many subgroups of order 2 inside a group where every non-identity element has order 2? How many are there? So look at the previous question. We have order of group is n. Every non-identity element has order 2. So number of subgroups of order 2 were n minus 1, right? So same here, how many subgroups are there of order 2? Are you following?
Yes.
Okay. Number of subgroups of order 2 in G is how many? It's n minus 1, which is 32 minus 1, 31, right? All right. So therefore, we have various extensions. We have
We'll have to
31.
add
Sorry.
those two elements, the trivial groups, trivial subgroups. So they corresponds to K and Q. Okay.
Exactly. So if I have H as trivial group, then KH is nothing but your K. If your H is G, then KG is nothing but your, sorry, Q, right? This we know. And therefore, if H is any HI, where HI is order 2, it will correspond to some Li such that K is to Li is 2. This is okay, right?
Yes.
Right. So there are 31 many subfields having index 2. So there are so many. And idea is just that how many subgroups are of order 2 there. It's enough. Yeah. All right. So let me go to another question. What are primitive and simple extensions? Primitive or simple? This is one thing only. What are those?
So I am yet to go through this concept. Primitive,
Okay.
simple extensions.
All right. Even I have not decided to discuss Kumar extensions. So okay, let me just simply give this definition. This is not very hard. So an extension, a finite extension maybe, a finite extension K over F is said to be primitive or simple if there exists alpha in K such that K over F is same as F alpha over F. Do you follow the definition first of all?
Is Q over
That means your K is nothing but F alpha. Maybe I will write this instead of that. So finite extension is primitive if a single element can generate your extension. Do you understand?
Yes.
Yeah. So only a single element is enough to generate your whole of extension K. All right. So I think idea is clear. Now looking at the second part, Q root 5 root 7 over Q, is it primitive extension? Can you write this as Q of some alpha or some alpha in Q root 5
root 5 plus root 7.
Exactly right. Very nice. So root 5 plus root 7 is the primitive element. It is the primitive element such that Q root 5 root 7 same as Q root 5 plus root 7. Very nice. All right. In fact, if you see for a characteristic zero field, maybe characteristic not equal to 2 is enough. You take two elements of the field such that root A, root B does not belong to field. Just like root 5, root 7 does not belong to Q. You take two elements. And if they are linearly independent over F, what is the meaning of linearly independent? Let me write now. So we say root AB, root B is linearly independent over F. That is, if there exists some scalar C1, C2 in F such that C1 root A plus C2 root C is 0 implies CIs are 0. Right? This is the same concept. Both CIs has to be 0. Or equivalently, you can say that if you are having if both CIs are 0, then it's clearly linearly independent. But if one of them is not 0, let's say C1 is non-zero, then you can write A as C2 by C1 root B is 0 implies A equal to minus C2 times C1 times root B. Do you understand, right? That means, let me write, okay? Hmm. So root A, root B is linearly independent over F is same as root B is not equal to C times root A for any C in non-zero C in F. You understand, right? This thing? That if a set is linearly independent, we see that if it is dependent, then you can write C1A, C2B is 0. Both cannot be 0 if it is dependent. And therefore, I can divide by one of the non-zero element and I can write A to be minus C2 by C1 times root 2, which is nothing but A equal to C times root 2. So if it is dependent, then you can find one scalar that one element is a linear combination of other. Scalar multiple of other, let's say, because our set has two elements only. So if it is linearly independent, you cannot write one element as a scalar multiplication of other element for non-zero scalar. This is okay, right? Hello?
Yes.
Okay. So maybe I'll keep these things. I will not remove. So if we want to understand the same concept, let's say for root 5, root 7, because we did the same computation for this. So why do we say that this is linearly independent over Q? So my claim is this. Because if it is linearly dependent, then root 5 is same as root 7 times some element of Q where Q is in Q, right? Because we are working over Q root 5 root 7. In fact, I should, what do I do? I think I should write in this way. Yeah, sorry. What did I write? Huh. If this is true, if this is true, if it is dependent, linearly dependent, then this should hold, right? This should hold for some Q. For some Q, it should hold if it is linearly dependent. Because dependent means there are some non-zero constants such that you can write this as 0. And one of them is non-zero, so you can write this as some, this time C prime. That I'm writing like this. Anyway, now this would give me that root 5 does belong to Q root 7. Do you agree?
Yes.
This
Q
would
root
also,
7.
yeah, Q root 7. This will also implies that this is contained in this, right? Or maybe I should write, if this belong to this, then you can able to write root 5 as A plus B root 7, right? Can you give me some contradiction from here, A and B from Q? Because if A and B both, if suppose B is 0, let's say, then A is root 5. Not possible because A is from rational. If A is 0, yeah, if A is 0, then root 5 is B time root 7. Is there any contradiction?
When both are non-zero.
Yeah, let's look at when both are non-zero. Okay, can we square? We can square, right? So square this equation. We will get 5 is A square plus 7B square plus 2AB root 7. Right? I can write this. Okay, now let me rewrite this statement. Just copy this. Okay, we got this. Yeah, we got
We get
this.
AB equal to 0.
No, we have assumed A and B both are non-zero. So in a field, it's a domain. This will always non-zero, right?
Okay.
So therefore, you can write this as
Now,
I'm
equating irrational part on both sides, you get AB equal to 0, which is a contradiction.
no, my AB is not 0. Sorry, I think there is some confusion. We got this equation and we want to say some contradiction, right?
No,
Yeah.
equating the coefficient of irrational factor on both sides. But not
Okay. Okay. That's also good. That's also good. So you'll get AB 0. It is not allowed. Exactly right. So therefore, these sets are always linearly independent. And not just this, you can also prove this. Not just this, you can also prove this. These are linearly independent. So in fact, they are helpful when you say that what is the degree of extension. So if we try to know the degree of extension, let's say for this over Q, then you are writing all the time like this. And you just have to know at each level. And this level you are getting equal, exactly equal, because root 7 does not belong here. And does not belong means it is linearly independent. Same thing, root 5 does not belong here. That will give you linear independent, that will give you dimension 2. Here, root 3 does not belong, therefore dimension 2. Here root 2 does not belong to Q, therefore dimension 2. So this linearly independent factor is very, behind this in order to tell the extension, degree of the extension. This is okay, right?
Yes.
All right, so I think mostly I have discussed everything. Let's do this question. I will not discuss Silo theorems because I feel like they are no longer required in the syllabus. So let's discuss the last question. If K over Q is the Galois group and K over Q is the Galois extension and the Galois group is isomorphic to Z2 cross Z2 cross Z2. How many intermediate fields between K and Q? This is something which is like more involved. This question is not simple. So maybe I'll quickly go. K over Q is a Galois extension. This is given. And the Galois group is Z2 cross Z2 cross Z2. In order to know number of intermediate fields, we will use fundamental theorem, right? That is the only key for us. So this group is in fact lower. We write G to be lower because it's a bijection is an invertible. It's a reverse. It's order changing bijection. If K is upper, group will be lower. This is identity. In between, you want to know the subgroups. So the question is knowing how many subgroups we have of order 2 and order 4. This is okay, right? Because our group is order 8. So number of subgroups of what orders are possible. We have to first know what are the possible orders of the subgroup Ken.
So 1, 2, 4, 8.
Yeah, Lagrange theorem says that this should happen. Therefore, order is 1, 2, 4, 8. So therefore, H is either identity G or H has order 2 and 4. Maybe or order 4. So we want to know number of, let's say, order 2 that are easy. I think that requires previous knowledge. Look at the group. It has very nice property. And you can tell me, I think, number of subgroups of order 2. How many are there? Yeah, can you tell me?
Number of subgroups of order
2. Order 2. In this group, look at the group carefully.
Z2 cross Z2 cross.
It has certain good property, which we have discussed some time back.
0, 0, 0, 1, 1, 1.
Yeah, elements are like 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, sorry, 0, 1, 1, 1, 0, 1, 1, 1, 1. I think this 1, 2, 3, 4, 5, 6, 7. Yeah. There's Z2 cross Z2 cross Z. Look at their orders. Can you see orders of each element?
0, 0, 0 and 1, 1, 1. It is a
Yeah.
subgroup.
Okay, it is one subgroup. Okay. This has order 2, right? Any other? I'm saying look at the order of every element, every known identity element. Look at the orders.
So as in the previous case, this is 1, 2, 3, 4, 5, 6. 6 minus 1 plus 2.
Okay, how many?
6 intermediate subgroups.
How many subgroups of order 2?
Because along with 0, 0, we can take any one of these elements.
Exactly. So how many?
That is 1, 2, 3, 4, 5, 6, 7.
Exactly. So we have total 7 subgroups of order 4. Well, it's little bit tricky that what are the elements of order 4. If you can see that also, it will be good. So how many elements of order 4 are there? Well, if you see, sum of two subgroup, I mean, elements of a group is always like sum of two elements will also be in the group. So if you take this, then the sum should also be there. So in this way, you will get this element. Let's say you call x1, x2. This is nothing but x1 plus x2. This is x3. This is nothing but x2 plus x3. This is nothing but x1 plus x3. This is x1 plus x2 plus x3. So you notice that you can make 7 subgroups of order 4 out of this. Same, 7 subgroups. How? Take, let's say this you call it E x1, x2, x1 plus x2. This is one. E x1, x3, x1 plus x3 is another. E x2, x3, x2 plus x3 is another subgroup. Then E x1 plus x2, x3, x1 plus x2 plus x3. And same, you will get total 7 subgroups of order 4. All right. So let's going back to the question. How many intermediate fields between K and Q is same as how many subgroups we have? Total subgroups are having either order 1, order 2, order 4 or order 8. So now can you tell me how many total subgroups, and that will give me how many total intermediate fields are there?
We have to see the degree of K over Q.
Well, let me repeat. In order to know subfield here, you have to know subgroup here, right? And we are saying that we have enough information about subgroup because any subgroup will have either order 1, order 2, order 4, order 8. And we have counted total how many subgroups of each order are there. That means we know total how many subgroups we have. Can you answer now?
14.
Well, 14 are there which are in between. So if I add up all, order 1 and order 8 also.
16.
Exactly. So we have 15 subgroups of G. Trivial, non-trivial, all.
So when they
Therefore,
ask intermediate fields, you will have to count that E and the K and F both, right?
exactly. So adding K, Q and L, all such set elements, number of such fields are total 16. Yes, this symbol is for cardinality. Cardinality of the set. All right, so I think with this I will just stop. So thank you.
Thank you very much.
Okay, recording.